Hey everyone, welcome back to AP Precalculus. This is lesson 1.7. Let's get right into it. All right, so there's no bell ringer today, but this unit we're going to be talking about rational functions. And I know last unit we only talked about polynomials, but rational functions is what this unit covers. And what is it? It is simply the fraction of two polynomials on top of each other, where the only restriction is really the denominator is just not zero because you can't divide by zero. So three examples of rational functions here. Could be anything. You could have f of x equals 2 over maybe x plus 3. Maybe you have a g of x, which equals x squared minus 3x plus 1 over maybe 3x plus 4. Maybe for example 3, you could have like an h of x, which equals 2x squared plus 4x minus 6 all over x cubed minus 7x plus 11, right? And so those are three different examples of just rational functions where they're all made up of two polynomials just piled on top of each other. So there's two different forms that you may find rational functions in. I'll be talking about these forms a lot, and it's really important that you get to remember what form do you need to find what, because some forms will be way more helpful than others. So the first one is standard form, and if you remember, think of the standard form of a quadratic equation, right? Ax squared plus bx plus c. That's kind of what we're going to want here, where everything is in standard form, all the polynomials are on top of each other, and everything is FOILed out. So there's no like x plus 4 squared or anything like that. No linear factors, just the terms arranged from the greatest term to the smallest term in standard form there. And this is going to be useful specifically today in finding end behavior and horizontal asymptotes, whereas factored form is really useful in finding other stuff that we'll talk about later. So getting into factored form, this is pretty simple. Think of the factored form of a linear or of a quadratic equation, right? You may have x minus c and x minus d, where x equals c and d are zeros of the graph. And so basically everything is going to be factored, right? Nothing's going to be FOILed out for you. These aren't going to be super useful today, but they will be in like the next 2 or 3 sections, I would say. But it is important that you know maybe how to go from factored form to standard or from standard to factored, and that is just using a lot of the algebra that you hopefully learned in Algebra 2. All right, so what really matters when looking at a rational function's end behavior, right? So we know what rational functions look like, but now we want to know what do they look like as we go to positive infinity, as we go to the right forever, or as we go to negative infinity, as x goes to the left forever. And the thing is everything matters, right? We love all parts of the rational function the same. Psych, I'm just kidding. That's not true. Only the leading term matters. Everything else is kind of redundant and useless and doesn't really give us any information about the end behavior of a rational function. For example, if we have this rational function here, we can essentially just cut off any lower power term and only focus on our leading terms in the numerator and the denominator. So you're looking at the leading terms of both, right? You can't just find the leading term overall, but that should be our rational, or what our rational function boils down to when looking at end behavior only. So what do we do once we find this leading term, right? Once you get the leading term of a rational function, you want to classify it as one of three things. It's either going to be top heavy, it's going to be equally heavy, or it's going to be bottom heavy. And all three of these are pretty self-explanatory, but to determine like what does heavy mean, we're going to be looking at the degree of both the top and the bottom polynomial. For example, for a top-heavy function, if you have 5x cubed over 7x squared as your two leading terms, this will be top-heavy because the degree is bigger in the top than in the bottom. An example of an equally heavy function could be if you have those as your leading terms, they're equally heavy because those two, the degree in the top and the bottom, are equal. And likewise, a bottom-heavy function, let's say this is your leading terms, is going to be where the bottom is bigger than the top there. All right, so let's take a look at each of the three cases and how to find their end behavior when they're top, bottom, or equally heavy functions. So the first one is when they are equally heavy, when the degree in the top and bottom polynomials are the same. And so if we take a look at this function here, the first thing you can do is like cross off anything that's kind of redundant. So we're really only looking at 4x squared over negative 2x squared, and this is going to be equally heavy. And basically, as we go to positive or negative infinity, what we can almost do is cancel out an x squared from the top and cancel out an x squared at the bottom, and this is going to tend towards 4 over negative 2, the ratio of the coefficients from each, the top and the bottom. And so as we get bigger and bigger, this is just going to go to negative 2. And so what this is going to look like is there's going to be a horizontal asymptote at x equals negative 2, and where there's a line where the function may approach it, but will never touch it. Right? So let's take a look at the actual graph. I just made that up. This is the actual graph of that function there. And so as we see, we have the line y equals negative 2 there. This is going to be our horizontal asymptote. And we'll learn basically what does that mean right now. And so what this means is as we go to the left forever, as x goes to the left, our y values are going to approach negative 2. It's going to get super close to that line, but never touch it. Same thing as we go to the right, right? These values are going to get super close to that negative 2 line there. Our y values will get super close, but never touch it. And so the first thing we see is there is a horizontal asymptote. We found that, and that will always be the case whenever you have an equally heavy function. The next thing we can find is our end behavior. So let's write two limit statements for this. The first one, if we wanted to describe this end behavior, we could say the limit as, we'll call this just f of x. The limit as x approaches negative infinity, so as x goes to the left forever, of f of x, this is going to give us y values that are very close to negative 2. Same thing here. If we wanted to write this as a limit statement, we could write the limit as x approaches positive infinity of f of x will equal negative 2. And that's because it will always just be a ratio of your coefficients, and that number will be your two limit statements for end behavior, as well as a horizontal asymptote. All right, so what happens when it's bottom heavy, right? Let's take a look here. You can almost cross those out. We don't need those in determining end behavior. So we are just left with x over 7x squared. You can cancel out an x from the top and the bottom and be left with 1 over 7x. And now, basically, what happens when we plug in either infinity or negative infinity into this function? Well, if we plug in, let's just say we plug in 1,000,000, right? Instead of infinity, this would be 1 over 7 million, which as a decimal is going to be super, super small. So it's going to get 0.00000 something, right? But it's going to basically be around 0. It's going to be so small that we don't even notice it. And if we just replace it with infinity, not even just 1,000,000 or 1,000,000,000 or a cajillion, right? It's going to get so close to 0 because any number over infinity is just 0. So remember, as a result, there's going to be a horizontal asymptote at y equals 0, and our two limit statements will go to 0 as x goes to positive or negative infinity. Now let's take a look at what this looks like graphically, right? And so this is the graph here shown. We obviously see that it's bottom heavy, but graphically, if we look as x goes to the right forever and as x goes to the left forever, we have this horizontal asymptote at y equals 0 there. So y equals 0, we have that horizontal asymptote, and what this means is that as we approach positive or negative infinity in our x values, our y values are going to tend towards 0. So if we write our two limit statements, we have the limit as x approaches negative infinity for this left-hand side. We'll call this g of x, just to switch up the names, is equal to 0. And the same thing here. The limit as x approaches positive infinity of g of x will be equal to 0. And so those are two limit statements as well as our horizontal asymptote, and that will be the case for any bottom-heavy function. All right, now this is probably the hardest one. What happens when it's top-heavy, meaning the degree in the numerator is bigger than the degree in the denominator? In this example, you can almost cancel those out. And now what happens when we have 7x cubed over negative 2x squared? Basically, this is not going to have any horizontal asymptote. It's also not going to have the same end behavior as you go to the left and to the right. What it will have is the same end behavior as this function simplified. So to find the end behavior, simplify this function. We can simplify the coefficients to negative 7 over 2, and then x cubed over x squared is just x to the first. And so this is a linear line, right? It's a negative slope linear line like that. Y equals negative 7 over 2x. This is very similar to, remember, lesson 1.6, y equals negative x, which is just that general shape right there. This is going to be the end behavior for that entire rational function there, which means as x goes to the left, this is going to go up, and as x goes to the right, this is going to go down. This is what this graph looks like. So obviously it's not as clear as a linear line in the middle, but we don't care about that. We just care what happens as x goes to positive and negative infinity. So writing our two limit statements, we have the limit, and we'll call this h of x. The limit as x approaches negative infinity of h of x, this is going to shoot up, so go to positive infinity. And then here, the limit as x approaches positive infinity of h of x is equal to negative infinity. So remember, when you have a top-heavy function, just simply simplify the leading terms as much as possible. So here we get negative 7 over 2x, and then find the end behavior of that polynomial. That will always be the case for any top-heavy function. All right, so there was a special case in case 3. I don't know if you could see it, but just know whenever the degree in the numerator is exactly one more than the degree in the denominator, we will have an asymptote, but it will be slanted. It won't be horizontal or vertical. It'll still have end behavior, so when writing limit statements, you're always going to want to refer to the end behavior of that simplified polynomial. But to find the exact slant asymptote, that's going to require what we learn later down the line using long division with polynomials. And so this is only going to be if we have, like, let's say in the numerator you have a degree of 7, and then in the denominator you have a degree of 6. Because 6 plus 1 is 7, this would have a slant asymptote. If we had a degree of 8 over a degree of 5, this would not have a slant asymptote because 5 is 3 less than 8, or 8's only 3 greater than 5. It's not exactly one more. It needs to be just one bigger in terms of the degree in the numerator for there to even have a slant asymptote. So here, this was that same function from before. This is the slant asymptote there. I won't give the equation or anything just yet. We'll learn how to find that later. But just know that that exists, which means this still obviously, right, goes down forever and this goes up. But as you go further and further left and right, these are going to really approach that that slant asymptote there and almost kind of hug that line a little bit. All right, so example 1, determine if the following rational functions have a horizontal asymptote, a slant asymptote, or neither. If it has a horizontal one, write the equation of it. And so remember, equations of horizontal asymptotes are in the form of y equals a number. It'll either be just a ratio of the coefficients if it's equally heavy, or 0 if it's bottom heavy. So let's do these together. The first one, our leading terms are just going to be 3x squared over 5x squared. This is equally heavy, so we take a ratio of the coefficients. So this is going to be y equals 3 over 5, and then this will have a horizontal asymptote. So that's that first one. The next one should be 2x over x squared, getting rid of your lower power terms. This is going to simplify to 2 over x, right? Or we just see it's bottom heavy, which means there will be a horizontal asymptote just at y equals 0. And that's the case with any bottom heavy function. And then finally, here, you don't worry about those. We have 2x squared over 5x. This is going to have end behavior the same as 2 over 5x, but no horizontal asymptotes. It will actually have a slant asymptote because the degree in the numerator was exactly one more than the degree in the denominator. So that one would have slant asymptotes, it would have end behavior, but it will not have a horizontal asymptote. Now we have D, E, and F here. And so for the first one, D, this is going to be an equally heavy function. So we should have a horizontal asymptote, but this is going to be at y equals 4 over 8, which is simplified should be 1/2. So that should be the horizontal asymptote there. Taking a look at E, this is going to be a bottom heavy function. Obviously the degree in the numerator is going to be 0, right? This is the same as 3x squared because anything to the 0 power is 1. So, or 3x to the power of 0 because anything to the 0th power is 1. So this should be bottom heavy. So there will be a horizontal asymptote. It's just at y equals 0. Same thing for F. This will also be bottom heavy. So there will be a horizontal asymptote, and at y equals 0 should be our answer there. All right, example number 2. Write the following limit statements to describe the end behavior of the following rational functions. Taking a look at the first one, those are our leading terms. This is equally heavy, so it should simplify to 2 over 6, which is 1/3. So our left-hand limit statement is going to be the limit as x approaches negative infinity, right, as we go to the left, of f of x equals 1/3. And the same for the right. Which is what's nice about these is that the left and the right hand limit statement, when there's a vertical asymptote, or sorry, a horizontal asymptote, will always be the same, right? These two limit statements should always be the same number for any equally or even bottom heavy function. Which brings us to B, which is a bottom heavy function, right? You can drop those and you have 5x squared over 2x cubed, but you still have x squared over x cubed, so basically you're going to go to 0. So our two limits would be the limit as x approaches negative infinity and the limit as x approaches positive infinity of g of x is going to be equal to 0. And that is our end behavior there. The final one, drop any terms that's not our leading term, and we have negative 3x to the 4th over x cubed. We want to simplify this as much as possible, so this just is negative 3x, and the end behavior is going to be very similar to y equals negative x from lesson 1.6. So that is going to be our end behavior. So the limit as x approaches negative infinity of h of x should be, as this goes to the left, this will go up, so positive infinity. And then for our right-hand limit statement, as this goes to the right, our function goes down. So this should go to negative infinity, and that should be our answer there. All right, for D and E of example number 2, We want to now write the limit statements given the graph instead of just an equation. So these I think are even a little bit easier. I'll throw names on these, but these should be, let's go g of x and k of x here. All right, so our left-hand limit statement should look like, as we go to the left forever, right, we are approaching a y value of 2, and the same as we go from the right, as x goes to the right forever, we approach a y value of 2. So our limit statement should be the limit as x approaches negative infinity and the limit as x approaches positive infinity for our left and right hand functions, or left and right side functions of g of x will both equal 2. Right, and then this one, as we go to the left and to the right forever, this is going to approach negative 1. So let's write those in here. The limit as x approaches negative infinity of k of x equals negative 1. And then the limit as x approaches infinity of k of x should equal negative 1 as well. That would be our correct limit statements for D and E. All right, example number 3. Which of the following rational functions has a slant asymptote? So remember, these only come when the degree in the numerator is 1 more than the degree in the denominator. So where the numerator is equal to the degree in the denominator plus 1. So let's take a look here. We have 2, a degree of 2 over a degree of 2. So I'm just looking at the degrees here. So that is not true. So it can't be 1. So I'll eliminate anyone with 1. Looking at 2, I have a degree of 2 over a degree of 3. That is not true. So we can eliminate 2. 3, here I have a degree of 2 over a degree of 1. This would work. So it could be either C or E. That really doesn't help us. Looking at E, here we see, no, wait, not yet, a degree of 4 over a degree of 2. So even though this is top heavy, 4 is 2 more than 2, not just 1 more. So it's not going to be 4, so we can eliminate E because it's not 4. So C should be our correct answer there. All right, so I know we've talked about and we've only looked at equations that are in standard form, which is nice and easy to tell end behavior. But what happens when the rational function is in factored form? We give up. Psych, I'm just kidding. You don't want to give up, right? You want to just convert it to standard form. But what's nice is when you're converting it from factored form to standard form, you are only looking for the leading term, right? We could care less about what happens to any of the lower powers, right? We even drop them. I've shown myself crossing off terms that don't matter when finding end behavior. So when we're going from factored to standard form, one thing that we can do is, if we have this polynomial as an example, we can take each term and drop any lower power inside the parentheses. And we basically then have, this becomes 3x squared times x cubed. That negative x stays there, times this positive x times x squared. So this is what it should simplify to. This becomes, remember, when you have, like, let's say 5x and this is cubed, you have to cube both terms there. So this would be 5 cubed times x cubed, which is 125x cubed. So in this case, we're going to have to square the 3 and the x to get 9x squared times x to the cubed. This simplifies to 9x to the fifth, and this becomes negative x times x squared, which is negative x to the fourth. That negative still stays out in front, and so this would be like the rational function, which would be an example of a top-heavy function. All right, so finally, example 4. For each of the following, determine if the given rational function has a horizontal asymptote or not. If it does, write the equation of the horizontal asymptote. So here we can almost cross this off And then this is already in the standard form, so we can cross off those two terms. So this really just becomes 9x squared over 2x squared, which is equally heavy, so it should have a horizontal asymptote at y equals 9 over 2, or 4.5. For this one here, we can cancel out anything that's lower powered, so it would be that positive 4 there, and then that 3. This basically becomes x times negative x over x squared, which is negative x squared over x squared. So this will be, yes, it should have a horizontal asymptote. This is because it is equally heavy, and it should just cancel into negative 1 over 1, or y equals negative 1. All right, C is probably the hardest one. Here we can drop that 3, drop that minus 4, that minus 2, that plus 5. We get 2x squared and that whole thing squared to get 4x to the fourth times just that x over x squared times x. This will simplify into 4x to the fifth over x cubed. This will not have a horizontal asymptote, right? It is a top-heavy function. It will also not have end behavior, so not applicable when the answer is no. Any questions on 4 or any of these examples, please come see me during office hours. I would be happy to answer your questions, and I will see you guys later. Thanks.